Hello everyone, together with my teammates, we are going to present SIVA MedBot, a medical symptom analysis system. This is our final project for the knowledge representation course, and it consists of a symbolic artificial intelligence system capable of analyzing medical symptoms and suggesting possible diagnosis with explicit justification. The problem SIVA method solves is a one we have all experienced. We feel symptoms and we don't know what we have before we can see a doctor. The lack of structured access to medical knowledge makes it hard to identify which condition may be associated with our symptoms or when it is urgent to seek medical attention. SIVA method addresses this in three steps. First, in analysis, the symptoms the user enters along with their intensity level. Then it reasons using formalized medical rules, evaluating 15 diseases simultaneously, um, and finally, it generates a ranked list of diagnoses explaining exactly which one is suggested. The domain we selected is clinical medicine, specifically primary care symptom analysis. We choose this domain for three main reasons. First, because it contains all five types of knowledge studied in the course, making it ideal for demonstrating a complete knowledge representation system. Second, because the relationships between diseases and symptoms present real ambiguity. For example, fever appears in flu, COVID-19, and dengue at the same time, which truly challenge the system reasoning capabilities. And third, because it has directed social relevance, the system covers 15 diseases over 45 symptoms organized by body, zone, and 8 medical categories.
I will explain what types of knowledge we identify in the medical domain and now we represent the in SIVA MedBot to design a knowledge representation system correctly. We first need to identify what kind of knowledge existing in the dominant. In our case, we for five types student in the course. The first in declarative knowledge. There are the concrete factor stored in the knowledge base. For example, flu is a respiratory disease favor as a make of 0.9 in flu or loss of smell in an almost exclusive symptom of COVID-19. The second is procedural knowledge. This is the know scope of the system. It represented the step the inference engineer follows. If they use a favor and code, they evaluate flu as a probably diagnostic. This knowledge lies in the Python function. The three is structured knowledge. There are the system relation better concepts. For example, flu is type of respiration disease of favor is symptom of flu, dengue, and COVID. At the same time, the relation from our system network. The fourth is heuristic knowledge. There are expert rules that a doctor and whole apply in instructive. For example, if the use report loss smell increments the COVID-19 score be 0.8 additional point, and because that symptom is almost exclusive, though that design and the field is meta knowledge. This is the knowledge the system has about it no limitation. For example, it DSM score are too low. The system notes the information is insufficient and async low confidence in system of generality and incorrect diagnostic. Once we identify the knowledge, the next step was selecting the most appropriate knowledge representation models to represent it. We select their models that work in a complementary way. what will K-urea approach. The first are semantic networks. We use them represent the structural knowledge of the dominant, the relational veteran, design symptoms, categories, and treatments. They are performed for this dominant because medical is everything relational, everything is connected to everything else. The second are rule-based system. These are the heart of the inference engineer. They represent procedural knowledge and heuristic knowledge trunk. If the rule we chose them over our models like case-based reasoning because we don't need really clinical cases. The knowledge is formulas take from medical literature. They allows offer the hits explainability. Every results can be traced directly back to the rule that generated it. The three are probabilistic models we use to represent the uncentrality of the medical dominant. Each symptom has a weight better when 0.0 and 1.2 indication how likely the symptom is to be presented in each dataset. This allows use to managing ambiguity. We multiplied desserts are similar simple.
The architecture of SIVA MedBot follows a five-component flow that works in sequence. First is a user who enters the symptom along with an intensity level, mild, moderate, or severe. Second is a web interface. The application deployed at a web, it is the access point to the system. It allows users to select symptom by horizon without any technical knowledge required. Third is the inference engine, the most important component. It has three functions. Analizar síntomas, which calculates the score for each disable by multiplies each symptoms, weight by its intensity factor. Aplicar heurísticas, which applies sequential adjustments based on expert medical knowledge. And calcular confianza, which assigns the confidence level, high, medium, or low. Based on the final score obtained, 4 is the knowledge base. The SIVA method.py file contain the fighting disables with their symptoms, probabilistic with and treatment. This is where all the formalizing knowledge of the system lives, and fifth are the results, rank links which confidence level match symptom and explicit justification for each diagnostic. Now let's look at how we formalize the knowledge. This section carries 20% of the total grade. Formalization happens at three levels. The first level is the logical rules of the rule-based system. Each rule has a formal structure, rule with a unique identifier if with the condition that must be met, then with the action the engine executes, and with indicating the expected confidence level. For example, rule gripe RC1 states if the user has fever and count or muscle pain, then increase the flu score by multiplying a symptom with by intensific factor. With high confidence, if the score reaches 3.0 or above, we also have special heuristic rules. For example, if the user reports loss of smell, then increase the COVID-19 score by 0.80 additional points. This rule exists because loss of smell is an almost execute symptom of COVID-19 and requires special treatment. The second level is semantic traits from the semantic networks. Each relationship is formalized um, a subject relation object. For example, fever is symptom or flu, or loss of smell is excuse of COVID-19. The third level is probabilistic formula. The score for each disabled is the sum of symptom weights multiplied by the intensity factor minus a penalty for missing case symptoms. For example, with severe fever, moderate good, and severe muscle pain, flu obtains a score of 3.55, which gives high confidence.
I will show you the system running live. As you can see, the interface organizes symptom by body sound, head, eyes, chest, abdomen, nose, and the body in general. This is directly implements the structural knowledge Sam mentioned. I'm going to select a classic flow case, fever with severe intensity, um, and musical pain with moderate intensity. Later, I will select cow, cow with cow with this intensity. And finally, I select mm, chills with mild intensity. In this part, mm, yeah. Um, when we analyze the inference engine evaluates all 15 DCs simultaneously using the formula Big explained. The result is flow in first place with high confidence and 100 relative relevance. The system shows exactly with symptom matched and the suggested treatment. This is the explainability of the system working in real time. Now, I I will add loss of smell with severe intensity. Um, um, and notice how COVID-19 moves the first place. This is heuristic role. Activating in real time differences of loss of smell increases the COVID-19 score by 0.80 additional points because it is a small exclusive symptom of that disease. That is heuristic knowledge in action. Now, the evaluation of the system using the 5 criteria from the course coverage. High level, the system exceeds the minimum project requirements with 50 diseases over 40 symptoms and complete KR life cycle coverage. Explainability. High level disease work grades entrench the system show which symptoms triggered each diagnosis, the confidence level, and when to see a doctor. Every result is fully traceable. Consistency. High level, the system is completely deterministic. The same symptom always produces the same ranking. The knowledge base is normalized and all weights are coherent with medical literature. Efficiency. High level response time is under 1 second. Computational complexity is on times, where in is 50 disease and M is the average symptom for disease. Adaptability. Medium level adding a new disease is as simple as adding one entry to the Python dictionary without modifying the inference engine. The main area for improvement is that it currently requires code access to make modification. To validate the system, we defined and executed 11 tests organized in 5 categories. In inference validation, we tested 3 cases. Flu with classic symptom of COVID-19 with loss of smell has the exclusive symptoms, and appendicitis with right side pain and has localizing symptom. All 3 based in consistency test. We verified that the system always produces the same ranking with the same input and that the weights are coherent. Loss of smell has a weight of 0.95 in COVID-19 and only 0.20 in flu but based. In rule verification, we confirmed that rule Hue COVID-1 increases the score by exactly 0.80 points, and that the case symptom penalty rule works correctly, but based in ambiguity case, we verified that when symptoms are shared between flu and COVID with hood, any differentiation the system doesn't force a definitive diagnostics. It shows, but with similar source based and exceptional handling, we tested that the system responds correctly when no symptoms are selected, when a large number of symptoms are selected once boot based. Finally, result that 11 days executed, 11 based. The maximum punctuation is 100. As the main conclusion of this project, first, SIVA MedBot demonstrates that it is possible to cover the complement TR life cycle in an academic project. Mm, from college identification all the way to system validation. Second, the hybrid approach of 3KR models provide more specific than any single model alone, each uncovered at different aspects of the medical domain. Third, and the most important takeaway, explainability is not a limitation of the symbolic AI. It is greatest strength online machine learning and knowledge representation system can justify very result in transparent and traceable way. In a domain like medicine, where the justification of conclusion is as important as the conclusion itself, this is a major advantage. For the system was developed, is live online, was approved by the process I validated, with 11 successful tests. To finish, SIVA MedBot is available at this link. You can try it right now. And thank you for your attention.